Hi, Chris. Hi, Maxim.
Hey.
Our speaker is Chris Klug. He's architect in Active Solution, and our expert is Maxim Arshinov. He's a teacher in Kazan University and co-founder High-Tech Group startup. Maxim.
Hi, Michael. So, hi, Chris. Also, I think that you are at your home now, right?
I am. I'm sitting at home alone, and hopefully my cat will shut up the entire time. Sorry if that comes in and starts making noises.
Well, cats are normally good. At least they're considered good on the internet. So maybe it might be funny.
Maybe we'll see.
Yeah. Okay. It's quite rainy here in Kazan. So what's the weather like at your place?
Well, if I look outside, which is right next here, it's all sunny and blue skies. So it's turning quite nice right now in Sweden. So I'm happy with that. Soon time to go out mountain biking.
Yeah, sounds good. Anyways, so we are going to be talking about solid principles, right?
Yes, that's the plan.
Okay, sounds good. And we agreed that if you guys on air have any questions, just text me on Telegram, and I'll let Chris know so we can answer questions during the talk, not at the end of the talk. So that's all I've got. Shall we start?
Absolutely. Let's get started. So I guess I'm going to be talking about the solid principles today, and I've been talking about the solid principles since TechEd 2014, I think it was. So I've been doing it for a very long time, but I haven't done it in a while. So it's going to be interesting for you guys, hopefully, and it's going to be interesting for me. And I do know that the introduction to the talk says that I will be showing you C# code of the principles, but I've actually, sorry to say this, I have removed the C# code and I've removed the code. And I've added another segment at the end to show some other stuff as well, which I find to be very interesting in today's development society. So we'll keep it simple and keep it out of code mostly, and talk about what the solid principles are. So my name is Chris Klug. As said before, I work at a company in Stockholm called Active Solution. I work as a developer / public speaker / architect / whatever you pay me to do. I'm a consultant, right? So if you pay me to do it, I will do it, except for the speaking gigs, which unfortunately don't actually pay anything at all, but it's fun to do. And I do enjoy sharing knowledge and sharing experiences that I've had along the way of my career. So the topic today, solid principles. And this is interesting. I normally do this talk in person, and I have this little check where I see how many of you do know different things, which is going to be a bit harder online because I can't actually see you guys. But you can look at it, and I will tell you why I'm doing these questions at the end. So first of all, how many of you have actually heard about the solid principles? That's normally that's sort of 90%, 95% of the room that I talk to. No matter the size or whatever, it's always about 95% of people have heard of all the solid principles, which is good, I guess. And then you move on and you ask, can name all 5 principles. And that's interesting because you go from about 95% and you drop down to about 40% of the room being able to name the principles. Which is cool because there's a lot of people have heard of the solid principles, but a few less know all 5 principles, which we're going to walk through today. So after today's session, you will have a good grasp of what the different principles are. And then you go to the slide where it says, how many of you can explain Liskov's substitution principle? And I love this question because normally I ask people to keep their hands up. So you start out with 95% of the room. Next question, half of those hands go down, and then you go to Liskov's, and all of a sudden, all but 1 or maybe 2 hands disappear in the entire audience, which is cool. And that's why I'm doing this talk, because people need to know the principles, not have just heard of them. Even funnier is that when I then ask the person who's got their hand up to come up on stage and explain it, that hand goes away as well. So I guess either they don't want to do it on stage or they don't actually know it. So what we're going to do is we're going to look at the solid principles. And first of all, if you didn't know all 5 principles, they are single responsibility principle, open-closed principle, Liskov substitution principle, interface segregation principle, and dependency inversion principle. And my plan is, let's just go ahead and actually go through one of the principles at the time, look at what they mean for us as developer, why we have them, and why they make sense. But before we do that, I just want to mention, so I've got a few questions over time about where do the solid principles come from? Who made them up, and when were they made up? Had they been around since the dawn of time when we invented computers? And they haven't. They have been around since 2000 or 2001 ish, in the form of solid. The actual principles can be a bit older, but the idea of putting them together to form the word or the acronym solid came in at around 2000, 2001 from Uncle Bob. So now you know that as well. But we'll start out with single responsibility principle, because that's the one that most developers, even if they can't name that principle, it is the one that most developers cling on to, because it says, well, actually, what it says is important. They cling on to it because it makes sense. But the actual definition, if you go to Wikipedia, is a class should have only one reason to change, right? That sounds fairly simple. However, one reason to change is fairly fuzzy, right? There's only one reason in all cases because we have changing requirements. Is that good enough as a reason to change? Is that a single reason to change? I don't think so. We should probably narrow it down a bit more. And I think the way to narrow single responsibility down to something that makes sense, in my opinion at least, in my head, is to go and say there can be only one requirement that when changed will cause a class to change. So we're moving it from one reason to change, because a reason is pretty big and fuzzy and so on. But if we move it down to one requirement that when changed causes a change, it becomes a lot more specific, right? Because now we can go and look at the requirements that we have. We've all gathered these requirements for what we're building, and then we can look at each one of these requirements and we can say, is there more than two requirements in our application that will actually affect this bit of code? And if there is, then we're doing it wrong. We should split that into two different things. My only concern and my only problem with that arrangement is I've been doing this for about 20 odd years now professionally, and I built my first web app in 1996, I think it was, the first one I got paid for. And so far, not a single one of my projects have started out with a predefined set of requirements that have been well documented and put down on in some form of paper or in a document where I can go and look at them and then qualify, is there only one of these requirements that will cause my class to change? So even though one requirement makes it better and more precise, we're still looking at something that's going to be really hard to implement as such. But we generally end up with saying, we as developers, the more experience we get, the more we can figure out these single responsibility things figure it out based on experience. We know what's going to change. We know how change happens through our software in most cases, and we can sort of do a good guess. But that's where single responsibility comes from. It's bringing your code, whatever unit of code you're looking at. It could be a function, it could be a class, it could be an assembly, whatever. But that one thing should do one thing very well. And that's what we're looking for. What about things like repositories, for example? Repositories is an interesting thing because they are ambiguous in a lot of cases. Because normally you could say, a single responsibility for a repository, that's fine, because the responsibility of the repository is to read and write data from the database, right? So the only thing that will change my repository is if I change the database. So if I build a repository that works with Entity Framework, and then I decide that, hey, I'm going to switch that out because Entity Framework was a bit chunky, I want to go with Dapper or some other micro ORM instead, then that is a single responsibility thing, because basically there's only one thing that can change my repo. That's a change of database access structure that I'm using or technology. However, that only works as far as your repository reads and writes to the same data store. If you, for example, decide to have a read data store that's optimized for reading and a write data store that's optimized for writes, like you do in CQRS, for example, but you still want to put one repo on top of it, then, whoops, shouldn't have touched that, then your repository breaks single responsibility. So you shouldn't do that. So this is a clear case of everything being contextual, right? So you have to look at each individual piece of code that you're writing, and then you have to make a decision on that piece of code within the context that you're working on at the moment. So if you're working on a repo in one project, that makes sense to make it as one thing, because you're doing read writes to the same SQL database. But then in a different project, you can't just go in and say, hey, this is a repo, that's single responsibility because it was that in my last project. Well, depends on your new project, right? So everything is contextual, which is important to keep in mind when it comes to these principles, and especially the single responsibility principle. So what are the benefits of single responsibility? Well, actually, the main benefit to me is you get smaller classes, so you get smaller things, right? Smaller things that do one thing really well. So you know that when X breaks in your system, or there's a bug in X doing X, it's fairly easy for you to narrow down on what component you need to look at to make the change, because there's only one thing doing that thing. And it also means that if you're single responsibility, or your code is single responsible, it means that when stuff is changing, it should be fairly easy to figure out that if I need to change this thing here, I won't affect a bunch of other things because they only have one thing that should change them. So small classes, simple classes are easier to maintain. And also, honestly, if you start looking at really single responsible things that are well structured, they're really hard to screw up as well, because there's often not a lot of advanced code in there, because you don't have a bunch of if statements and else statements and weird forkings in your code, because that is probably not single responsibility in a lot of cases. So it gives you simpler code in a lot of cases as well. That's the single responsibility part. That's the S of the solid. So the next part, if we move on, is open-close principle. The open-close principle, I don't care if most people are scared of explaining Liskov. To me, open-closed is much, much harder to explain and make sense of, to be perfectly honest. So open-close principle says software entities should be open for extension but closed for modification. Okay, so we need to write code that we can make better without actually changing the code that we have already written. Yeah. Okay, that's going to be an interesting task as a developer, and it comes with a bunch of questions. And also, it's also pretty fluffy. This definition here of software entities should be open for extension but closed for modifications. There's so many things in here, but if we skip, I have a different definition, which is once it's done, it's done. Once it's done, it's done is pretty simple. It's like once you've written a class and it does whatever you need it to do, you stop touching it. You don't work with it. You close it down and you don't play with it. And the cool thing about that is that it has a bunch of really cool benefits, because if you go and say, I've written this class, it's done, it does what it's supposed to do, and you never go in and make any changes to that code, it can't break. You can't break it because you've never made any changes to it. So it will always work the way you intended it to. However, there's a bit of debate here, because open-close principle comes in two forms. It comes in Meyer and polymorphic. And Meyer comes from a French guy, I think he was, called Bertrand Meyer, who invented Eiffel, the language. And he came up with this idea of open-close principle. And he has the original gangster when it comes to open-close principle. He's the guy that coined the thing, and he's the one that says how it's supposed to work. And he says that it's all based on inheritance. So you write one class, and once you're done with that class, you lock it down and you say, this is now done. I'm going to do a big tick on that, and I'm going to be done. And then whenever we need to go in and make changes to it or add stuff to it, we inherit that class and we add more stuff to it. Which is cool, because he's basically saying that a class should always stay the same, but you can add more stuff to it. And potentially you can make some stuff virtual or override it in your inherited class, as long as you don't change the intent of the base class and what the base class is doing. And then we have polymorphic, which is kind of open-close as well, but it's actually 100% opposite of what Meyer is saying, because polymorphic says, let's have an interface, and then we implement that interface. And then whenever we need a new implementation, we do a new implementation of that interface. It's still kind of open-close, because I've written this one version of my interface, and that happens to be a SQL repository, coming back to the repository example. And then I go and say, hey, I'm going to have to go and make changes to this. I'm going to add logging to it. Then I can go ahead and I can inherit that class. Or sorry, let's not go and add logging, sorry. Let's go and create a Dapper implementation instead. So I'm going to do micro ORM instead. So instead of inheriting the class, instead of inheriting my SQL instance and get all of that functionality together with what I'm doing, I go and say, I'm going to create a brand new class, not messing around, not changing the old one, just creating a new instance. Very open close, right? I created it, I made it, and then I'm done with it. And then I create a new version of it, and I use that instead. The difference here is that Meyer says, let's take all of the functionality of the original class and extend it, which means, hey, it's going to have the same functionality, but the API or the API of the class is going to change, because it's going to have new functions or new properties on it. Whereas polymorphic is the inverse, that says, we're still going to close it down, we're not going to make any changes, but what we're going to do is we're going to have an API that's the same, and you implement the API, but we never inherit any class, which means that we're not getting any functionality. So it's kind of the same in the way that we're not changing classes, but it's inverse in the way that Meyer says, let's keep the functionality and extend it, whereas polymorphic says, let's keep the interface and do whatever you want behind it. Benefits to this, well, if you've created some code and it does what you want it to do, and you don't change it, it's not going to break, right? Fairly simple process. If it's done, it works, it won't break. Every time you open a piece of code and you make changes to it, you have the potential of introducing problems. You have the potential of introducing bugs, breaking stuff, and so on. If you don't touch it, it won't break. So that's the benefit of open close principle. So that's SO, open close principle and single responsibility. The next one is Liskov substitution principle, which is funny because this, as I said, this is the one that people seem to be shying away from when you start asking, can you explain it? No. And that's because the definition of Liskov substitution principle is, bear with me, let Qx be a property provable about objects X of type T, then Qy should be provable objects for objects of Y of type S, where S is a subtype of T. What did you say? So this is a very precise form of what Barbara Liskov talked about in her keynote at Data Abstraction Hierarchy. And it's kind of brilliant. And it's also, if you're not a mathematician or really, really clever, you look at that and you go, what? I have no idea what that means. And especially if English is not your native language, then you look at that and you go, holy moly. So if we go and change that into what I would say, if I'm going to paraphrase it in my language, I would say a subclass should behave in such a way that it will not cause problems when used instead of a superclass. So what Liskov is saying here is she's saying, whenever you take a superclass and you subclass and you create a new class, you inherit from something else, make sure that whatever you do in the new class doesn't cause problems if you use that class instead of the superclass. So if you have a parent class that is used in a system right now, make sure that when you inherit that class and you do whatever changes you want to do to it, make sure that you do those changes in such a way that if you replace the old class with the new class, nothing breaks. Makes sense. And how do we do that? Well, what Barbara Liskov came up with was a few rules. So she says, I have these rules, and if you follow these rules, I'm going to make sure that your code doesn't break. Ish. Yeah, it's a pretty bold statement. So what she's saying is, first of all, contravariance of method arguments in a subclass is fine. And covariance of return types in subclasses are fine. What does that mean? Unless you are very familiar with contravariance and covariance, this code is not very understandable, or this text is not very understandable. Translated into English, I can do it in English and Swedish, and I do believe that English would be better for you guys. So what it's saying in English is method arguments in a subclass can be changed to be less specific. So basically, if you have a class and you have a method that takes in a sports car, you can, in your inherited class, change that parameter to be a car because sports car inherits from car. So any existing code that is out there will always pass in sports car because that was the previous requirement. And if you change the code to accept both sports cars and cars, then you're fine. It won't break. And covariance in return types is the opposite, and basically says, in whatever you return from your subclass, you can return more precise objects. So if the class used to return car, you can now go and return sports car because the sports car inherits from car and you're good to go. So she's saying as long as your input and your outputs are formulated in such a way that existing inputs would always work and new output will always be compatible with existing outputs, you're good to go. Cool thing about this rule is that in C# we can completely ignore it because it is literally impossible to make changes to your class methods when you inherit something or you implement an interface, because the signature of your class always has to be the same. You cannot change the signature between two classes or when you inherit it. So in C# it doesn't matter. Somebody did show me an example that actually managed to break this, but honestly I can't remember the example and it was weird. So ignore this rule if you're in C# land. If you're in JavaScript land or something else where it's a lot more loose, then good luck. Please read into this and use it as much as you can. Another rule she has was no new exception types are allowed to be thrown unless they are subclasses of previously used ones. Another pretty simple and basic thing to understand here, because if you have a piece of code that you're using today and it is throwing a couple of different exceptions, code that is using that unit, that class, will know how to handle those exceptions. They will probably have try-catch clauses around it, knowing that I need to catch this argument exception, I need to catch this other exception over here. If you then inherit that class and you replace the old class with your new inherited one, and you all of a sudden start throwing exceptions that aren't subtypes to the ones that were used before, then there's no way for existing clients to figure out how to catch them, right? They will have try-catch for the previous code because that is what they knew, and then you add this new implementation, all of a sudden there are new exceptions, which is going to fail. However, if your new exceptions inherit from the same exceptions that were thrown before, you're good to go because all old clients that use your code will still be able to catch your new exceptions, because due to inheritance, they will just catch it as the parent exception instead of the one that you're actually throwing, so it won't break existing code. And then she says, preconditions cannot be strengthened in the subtype, and postconditions cannot be weakened in a subtype. Once again, really funky English. It could be expressed so much easier for normal people, but Barbara Liskov was a mathematician, data person that was probably brilliant in a lot of ways. I'm just not smart enough. So what she's saying is, when you inherit a class, you cannot add more conditions to it. You can't set up new requirements. So if you have a class that requires you to set property A before you can call method B, you cannot go and change that class to say that, hey, you have to set property A and B before you can call method B. So basically, anything that you could do before you inherited has to be possible to do after you've inherited it as well. So you can't add new conditions, you can't add new requirements. And also, post conditions cannot be weakened comes back to same thing, but kind of the inverse, saying when you inherit a class, you cannot make changes to it in such a way that what you could do before, you cannot do more things than you could do before. So you can't go ahead and say that, hey, I want to change this thing. You couldn't do this before, so I'm gonna, because previous requirements said that you weren't allowed to call this method in these cases. So for example, you're only allowed to call this method on Thursdays. You can't go and say, hey, in the next version, I'm going to allow you to call it in both Thursdays and Wednesdays, because that's weakening post conditions. So basically, keep in mind what you could do before and keep the classes or the module you're working on to the same standards that you had before. And then finally, the last thing she had was the history constraint. And the history constraint is all about mutability. So what Barbara Liskov is saying with history constraint is, if the class was immutable before you inherited it, it has to be immutable when you're done with it. Or rather, at least the properties that were immutable needs to be immutable in your new version. And anything that was mutable in the previous version has to be mutable in the new version as well. So it's just mutability between parent and subclass needs to be the same for the things that are defined in the parent. So there's an interesting thing. If you ask somebody to come up with an example for Liskovs, there's only one example out there. There's literally one example that everybody uses, and it's this one. And normally I'll have a raise of hands here, but once again, it's kind of hard online. But you can have this in your head, and you can make up your own mind and then see if you're right. Should a rectangle inherit from a square, or should a square inherit from rectangle if you were creating shapes? So this is, I know this is a stupid example, but it's actually the only really good one that's out there. And whatever you've thought of, if you think rectangle should inherit from square, you're wrong. And if you think square should inherit from rectangle, you're wrong. Neither of these are actually possible with Liskovs, because if you inherit a rectangle from a square, you're weakening post conditions, because you're now saying in a square, the sides have to be equal. So the height and width has to be the same. If you inherit and change it into a rectangle, now you're allowed to change things. Now you're allowed to have a different width than a height. So you're weakening post conditions. And if you go the other way around and you inherit square from rectangle, you're strengthening preconditions. So now you're basically saying, hey, wait a minute, you used to have width and height being different things, but now they have to be the same. That is going to break whatever code is out there, so this is not legal to do. So they should all inherit from shape. And I have this comment down here. I've got Telegram at the bottom here. So if you see me looking down once in a while, it's just me checking if there are any questions. Somebody, Lev, said nothing should inherit, and I'm not going to go as far as saying nothing should inherit from anything, but I do agree with inheritance being the bane of a lot of developers' life, because they end up with these long inheritance chains that are brittle and hard to work with and everything. So I do tend to stay away from inheriting things, to be perfectly honest. But anyhow, this is a good example of Liskov's rectangle square, very, very simple to understand in most cases. And then you get this question, what about abstract base classes and interfaces? Well, interesting question. Because if Liskov says that you're not allowed to make changes to a class because it based on what was done in the base class, if you have an abstract base class or an interface, you have no idea what the previous type did, because the previous type didn't do anything. And that's where Liskov actually says in her little statement there, it says property provable. And provable means we can actually verify a value. And with an abstract base class or an interface, you cannot prove anything. So Liskov doesn't go in with abstract base classes and interfaces at all because they're not provable as such. And the benefits, well, you stop breaking code. That's fairly good thing. If you follow these rules that she has, you're unlikely to cause problems. So you got single responsibility, keeping our classes really small, and then we do open-close principle, saying that once you're done with a class, you should not touch it, so you should inherit it instead and make new versions of it, which then brings us to Liskov that says that when you've got lots of little small classes inheriting from each other, then we need these rules so that we don't cause problems when we use them. So benefits should be less problems, fewer bugs introduced, and so on. Also a pretty cool thing, if you're I read something about Max actually having written about tests, and I'm not a TDD developer, but there's a cool thing with Liskovs and tests, because if you have a really cool big suite of tests for your code, if you can put your code, the parent class, through all of those tests and they work, and then you take your inherited class, your subclass, it should be able to be put through all of those tests as well, and they should at least not break. If you've made changes to the code, we'll come back to that, but that's at the end. But if you've made changes, obviously the tests might fail because they might see different results, but your code, your tests should never fail. Which also means that if you're doing Liskovs and open-close principle together, it means that you can write all your tests, and then once you're done with your code in your open-close case, then you can turn off all your tests and save your CPU cycles, because you don't need to test that code ever again because it doesn't change. And then you do follow Liskov, so when you do a new version of that class, you make sure to run that class through your tests, and they should still work more or less. So it simplifies the testing phase as well, with less changes to your code and less CPU cycles going into your tests. Completely separate benefit than what it was intended for, but that's my benefit. Then the next one, interface segregation principle. This comes kind of out from a corner, because you've got single responsibility, and with that you end up with open close because you're lots of small classes, and then because you do open close and not change your classes, you get Liskovs because you get all of these inheritance, and then you got interface segregation principle, which doesn't actually build upon the previous ones at all. I think SOL kind of builds on top of each other and have good reasoning to be thought of together, whereas interface segregation principle is a bit different. So interface, so first of all, before I go to the next slide, it is no, ignore me. Next, wasn't this principle I was supposed to say something about. So let's keep it to this, sorry. Clients should not be forced to depend upon interfaces they don't use. That is the definition of interface segregation principle. And being me, my initial reaction is, who cares if a client gets a bit more than he needs or she needs? They can just ignore it. If I give you an interface that has more features on it than you need, then who cares? Just don't call those features. That's nothing more complicated than that. If I go to my corner store and I buy an ice cream, and the guy in the corner store gives me 2 ice creams but charges me for 1, I'll just be happy. In software development, not so much. So what we are trying to say, or sorry, what Uncle Bob is trying to say is, breaking down interfaces in smaller pieces makes them easier to implement and offers much more control over who sees what. So making it, you pull it down to a small interface, not because you don't want to give a client more to work with in a lot of cases, but mostly because they're actually it's a lot easier to implement. So having small interfaces makes it easier for you to implement them and get over with. But then on top of that, you can also go down and say, hey, I'm gonna scale this down so that this thing over here doesn't actually need to have the delete method because it's not supposed to work with delete. And then I have a specific interface for management that has deletes. But I find that being a weird way of, it's like, oh, I'm going to use my interfaces to control who gets to delete stuff in my code. To me, it just points at you not trusting your developers. So if you don't trust your coworkers with your code, then you've got other issues. Because if you're saying that, hey, by giving my coworker over here an interface that doesn't have a delete method, he's not going to delete stuff. I trust my developers not to delete stuff, even if I give them an interface that allows them to. And also, if the developer wants to have your delete method, they probably have access to your database anyway and will go in and delete anyway. So unless you have little gnomes coming in at night developing stuff when you're not at the office, then I don't see that being a reasonable reason in a lot of cases. But sure, there are cases where this makes sense and basically locking off who gets to see what. So what's the benefit of doing interface segregation principle? Well, you come back to that idea of a small interface being a lot easier to implement. And it allows you to segregate things down. And here I agree. Lev wrote again, he said, I think it relates to single responsibility. And that's the thing. Yes, it does. It's so correct that single responsibility principle, if you've done that right, your class already has a single responsibility, and your interfaces should not be able to grow into these unwieldy big things, because in that case, you're breaking single responsibility, which is why I'm not a big fan of the interface segregation principle. I'm not, because if you've done the S properly, then interface segregation is not going to be there. But I do have a very awesome example of breaking it and screwing things up, and it's breaking everything. It's not just it's breaking interface segregation principle, it's breaking the S as well for single responsibility. But I don't know if any of you were around in the old ASP.NET days when there was and because of that I forgot the name of it. There was an authentication thing that you could plug into. It was like an authentication service that you would implement. Membership provider, that's the name of it. So the membership provider was this really cool thing. I think it was in web forms days, where you would plug in a membership provider, and that would handle everything that had to do with logging in and logging out and so on. And Max is writing now, membership was a nightmare. Yes, it was. No one. Well, yeah, I implemented it a ton of times because of the job I was in at that point. And the problem with the membership provider is you inherited this base class called membership provider, which was abstract. And then you'd go and implement that, and you'd go into Visual Studio and say implement base class, and you'd get 27 different methods that you had to implement. And then there was everything from password validations, password complexity validation, to retry blocks, and user information updates, and email validation, and phone validation. There was like a gazillion things baked into it, and you had to implement everything. Well, actually, you didn't. Because if you didn't want to use any of that, if you only wanted to log in, which was what I built in a lot of cases, like, hey, I have an old database, I want to make it possible to log in using the old database, and the membership provider is just a nice way of doing it, you only had to implement 3 methods. All the other methods you would just leave as throw new not implemented exception, and the code would still work because you never called that part of the code. But it is such a breach of single responsibility and interface segregation principle. If they had broken it down, I could have implemented that one little interface for logging in, and I'd be done with it. So yeah, obvious case of breaking interface segregation principle, but also that comes with the breakage of single responsibility as well. So they tie together. The last principle is dependency inversion principle. And also, first of all, is dependency inversion principle, not dependency injection principle. Dependency injection is a technique, not a principle. And That's why it's called dependency inversion. There's an echo I hear now. Am I causing an echo? Sorry, don't know what that is in that case. Hopefully it's not too bad. So what does dependency inversion principle say? Well, dependency inversion principle says high-level modules should not depend on low-level modules. Both should depend on abstractions. Abstractions should not depend upon details. Details should depend upon abstractions. Okay. Another one of these fluffy, fantastic descriptions of something. So basically what we're saying is that abstractions should depend upon abstractions and details should depend upon abstractions. Are we going to have only abstractions in our applications? Are we not going to implement anything? And that's not what they're trying to say at all. It's just me being dumb, right? What they're trying to say is, if you make sure that your class, that well, say a class, doesn't depend on a specific implementation, it becomes easy to change things around, right? Because whenever you have a class that news up or creates a new instance of a specific type, anybody using that class will also have taken a dependency on that thing that was created inside of that class. So you're forcing everybody, every single client of your class in the future is forced in to depend on that specific implementation. So for example, if you're doing file system things, so here's a simple app that I haven't built. I've PowerPointed a simple app, right? There's an app, and the app in turn depends on a persistor, which is a class, and the persistor class goes ahead and news up a system IO file. So the problem here now is that my app wanted to take a dependency on persistor because persistor persists stuff. That's all I needed. I needed to persist things. But the problem is, because persistor takes a dependency on system IO file, my app has a dependency on system IO file as well. And it's not too bad with system IO file because it's a part of the framework, but imagine that it was persistor taking dependency on a separate NuGet package. Then all of a sudden my app is dependent on that NuGet package as well. And if that NuGet package just happens to be JSON.NET, then you're screwed, because there's a new version every 4 seconds of that thing that breaks stuff. It's not as bad anymore. They've solved a lot of that. It used to be that whenever James released a new version of JSON.NET, it would break things because there was version incompatibilities, and you'd have these binding redirects to make it work and all of it. And a lot of this came down to my application taking a dependency on something that took a dependency on JSON.NET. And if then I took a dependency on JSON.NET as well, but they were 2 different versions, we end up in this versioning hell that is really, really hard to work with. So remember that whenever you take a dependency on something, anything on top of your class, anybody with a dependency on your class will have a dependency on whatever you took a dependency on as well. So what we can do instead is this. If we instead break everything apart, and we make sure that my app depends on an abstraction, so it depends on iPersistor instead of my actual implementation persistor. And then the persistor class takes dependency on an abstraction, in this case iStorage, and then my storage implementation uses system IO file to write to disk. A lot more classes and their interfaces involved and everything, but it means that my app will take a dependency on iPersistor, which means that I can replace the persistor to whatever persistor I want in the future because I haven't forced anything. And since my persistor takes dependency on iStorage, I can change out the implementation of iStorage in whatever way I want, because without affecting my app or the persistor as such, because hey, I only need the abstraction, I don't care of your actual implementation. And then, okay, there is a point where my app will have to figure out how to combine these things. So my app, when it starts up, would have to go and say, okay, I need an iPersistor. Then I'm going to create the version of iPersistor that I want, which happens to be my persistor. And then that needs an iStorage implementation. then I have to create a storage implementation and inject that into inject it into my persistor. But the cool thing is that there's now not, my app is now not dependent on system IO file and the disk implementation. It can just as well go and create other things, which means that we have inverted the dependency. So I don't become, as a parent class, I don't get, or higher level class, I don't get dependencies forced upon me by the classes that I use. Instead, the classes that I use will ask for whatever dependency I want to inject into them instead, which makes it a lot better because we can move things around, right? So I can change the implementation. If I decide that I don't want to store stuff on disk, I want to store it in a blob, in a cloud, then I just give it another implementation of iStorage. And this brings a very interesting point, which is people look at me funny when I say, but the worst thing you can do in this case, and solid principles, when you write C# is to use the new keyword. Anytime you use the new keyword, you're screwing yourself over. I'm not sure I'm allowed to say that, but I'm going to say it anyway. Or you rather might not be screwing you over, you might be screwing your colleague over, because whenever you new up a new class, you're also saying that any class in the future that takes a dependency on my class will, per definition, also take a dependency on the thing that I'm newing up, which is really, really crap from a maintainability point of view and the ability to move things around. And it often comes down to everybody say, oh, well, also it's not testable. Okay, that's whole different story. I'm happy to have that discussion at some other point. And testing forces us in a lot of ways down through a dependency inversion situation because we want to be able to test our code properly. But that's not why we do it. We could get away with writing more integration tests and thus test our code and still have hard dependencies. That would be fine as such. But the biggest problem is, to me, is the whole I can never change it. The fact that I'm forcing somebody above me to take a dependency on whatever I knew up, yeah, that's a bad thing. But from a practical point of view, my biggest concern is that I can't move things around. I can't change things, which is kind of annoying. So the benefits we get from dependency inversion principle is the way that we can move things around, right? We can change things. I take a dependency on this class here because I want to use that class. But by taking a dependency on that class, I'm not taking another dependency. That thing just says, hey, I have this interface that you have to give me because I need this thing here. It's an abstraction. It needs to be able to do these things. Please tell me what to use. And then I can tell it what to use. And it opens up the ability to do things that the person who wrote the class initially had no idea that it was going to be possible at all. The guy writing the persistor class today has no idea that in the future, if he just depends on iStorage, there's going to be quantum storage in the future that stores data on clinically grown brains in a lab somewhere in Alabama or something like that. I have no idea, but you get the point. You can do whatever you want, and it opens you up for future changes as well. Not to mention really cool effects. Like when I used to live in New Zealand, I built this camera system. It was a physical kiosk that you would put in bars, and it would you could pay a few dollars, and it would film you and take photos, and you could write a message, and they would post those films and photos onto your Facebook page. It got revamped into something you do at weddings, and they created a little book for you and so on. So it's a really cool idea, but it's a lot of hardware, right? It had a coin mech to take care of your coins when you paid for it. It had a DSLR camera. It had a video camera. It had a touch screen. It had all of these hardware things, and a very specific printer as well to print the cards so you could get them in your hand as well. And it made it hard for me as a developer to build this thing because it was hard for me to debug on the hardware that they had. I didn't have access to a lot of the hardware, but we made it so that everything was dependency inverted. So I could go ahead and I could inject a fake camera, and I could inject a fake coin mech, and I could inject all of these different scenarios and try different things. and it just worked. I could run it without having all the hardware. And when the client came to me and said, oh, we have to change DSLR cameras, and when we do that, because the old ones aren't produced anymore, there is not an SDK, the old SDK doesn't work anymore, I could just go and write a new DLL file that implemented the iCamera interface with the new SDK for the new cameras, and then the client could actually use a config file and say, so run the software on this kiosk here, but that has the new camera, so use this DLL file for that implementation. And this is an old kiosk, it has the old camera, you need to use this implementation. And we could match things up because we had different hardware in different places, for example. So it has all of this massive flexibility. And as you can hear from my voice and my excitement, I like dependency inversion principle a lot. However, it also comes, so solid principle comes with a few little discussion points here as well, or some considerations to take into account. Sorry. So first of all, with solid, it is very easy for you to start over-engineering and optimizing things for the solid principles way too early. It takes years to learn how to do solid principles in a pragmatic way. You should start out by being pretty firm, solid, until you learn enough to understand when you can sort of bend the rules a bit. And that comes with pure experience. That's all there is. So you do often end up with a overly complex system in the beginning, and then slowly you learn that, hey, I'll cut some corners here because I don't think that's going to be a problem, and cut some corners here because I don't think it's a problem. And then in the future, when you realize that it might have become a problem, you can always refactor and make it easier. But yeah, you do end up with over-engineered and prematurely optimized systems in a lot of cases with solid. That's just the way it is. Readability. Yeah, code becomes a lot more readable, right? Because everything is single responsible, very small classes, easy to find, easy to see what they do, easy code to read because there's little code in the classes. They're often less than a page long, so you can read it all in one screen and so on if you do it right. Absolutely. Problem is that when you have dependency inversion, it means that you have a bunch of interfaces and you have dependency injection going on probably in your application, which means that you don't know what parts are going to work together until you do it at runtime. Which means that readability, yeah, definitely. Each class becomes very, very readable, but your entire system becomes this blob of, I have no idea what configuration is going to run in production, so I'm going to have to test and run it and see if it works together, and you jump between, so Control F12 in Visual Studio is your friend, which is jump to implementation, because there's only references to interfaces all over the place, and then you don't want to go to the interface, you want to go to the implementation and so on. So readability, sure, on a small level, on the unit level. Readability as a whole, not as great, to be perfectly honest. Debatability. You and your friends will be debating this during lunch because there's no right and wrong answers in a lot of cases. It's always a discussion because it's all contextual. So you will be debating, should we do X, should we do Y, because there's always different ways of doing it. My suggestion is don't bring a knife to a gunfight. Always go with guns if you have to. No, I didn't say that seriously. Don't start arguing about it, but you will probably have healthy discussions about it. And my thing here would be, I tend to lean towards people with more experience over highly educated new people right straight out of uni, because in this case, there's a lot of, I have seen this before, and experience and context and so on that comes into play. And also the last one, 50 versus 230, is that the code examples I normally show in this presentation goes from being 50 lines of code to being 230 lines of code because I've turned it into solid. I also added a few new implementations, so it's not quite true, but I do think it went from 50 to 150 lines of code just because I started breaking things apart and I added dependency inversion and so on. So you do get more code, but I'm not saying that more code is worse. I know that a lot of people say that code is cost, right? There's cost involved in code, and we're paying depth on the number of lines of code we have. And yes, we kind of do. I agree that lots of code is not great, but I'd rather have a bit more readable, understandable, safe, solid code than I would have smaller amounts of code that was hard to read. I will always lean in that direction. But, so this is where I'm going to go off the rails. And this is why I've removed my code samples. And this is what I've been dreading to do for a while, and why I haven't actually done this presentation in, I think, about a year. Before that, I've toned it down a bit as well, because I've come to the conclusion that having talked about the solid principles for years now, and adhered to them and listened to them and implemented them and lived a lot of solid stuff, I've started to question them. I've started to question them a whole lot, and I will explain why. And this is not because I want you to go and say, hey, I'm not going to use solid. Solid is shit. I shouldn't use it. It's broken. Blah blah blah. We now have JavaScript, which is much better and doesn't have to be solid. That's not what I'm saying at all. But I want to bring a bit of other information into the discussion as well. So let's go and look at it. So single responsibility principle being the first one, and I believe in the intent of this principle, but as Dan North said, the pointlessly vague principle. I kind of enjoy that definition, because it's very vague. It doesn't say anything. A class should have only one reason to change. It's so vague, it's not even funny. And I tried to make it better. I do agree. I did try to make it better and say only one requirement should have an effect. But interestingly enough, when you start talking to Uncle Bob himself about this principle, it changes. Because Uncle Bob says this principle is about people. And now I start going, what is he talking about? Well, what he is saying is a version of what I'm saying, but he says this principle is about people, and it's about C-level people, apparently. So CTOs and CIOs and so on. And they make the decisions on your code. So somebody up in the food chain, somebody who makes more money than you do, makes decisions, right? And there should only be one person responsible for one part of your code. So that you should never have to go and ask two people about your code. So a code should only take input from one person. And it also means that if person A, your CTO, comes and says, hey, you know that piece of code that I'm doing here, that I told you to do here, I want you to change it and change the functionality to this, that should not affect the other code that the chief financial officer has said about something, because they're two different responsibilities. So according to Uncle Bob, it's about people. And I find that to be I hear what you're saying, but no. What I think we should say is more, this is me paraphrasing a lot of stuff that I've read and my own opinions as well. And it's like, aim for high cohesion and low coupling and refactor if necessary. So what we're saying with single responsibility, without having that vague, only one responsibility, blah, 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 try to make sure that whatever you put into a unit of code has high cohesion. And high cohesion means that they are coupled together. No, sorry, they're not coupled. They intended to be working together. They should be one thing. So high cohesion means that things that you feel belong together should be in one place. And when you get low cohesion, you get high coupling. Because all of a sudden, if you have low cohesion, and you get high coupling, because one class is tightly coupled all of a sudden to another class, and maybe another class, and maybe another class, because they really are supposed to be together, because the code that you have in class A depends heavily on code in class B and C, then maybe they should be together. So instead of having your code spread out with tight coupling between different classes, you might want to have a look at getting them into one class and have high cohesion inside of that class, and then less coupling between classes. And then refactor when you need it. So you go with one decision today, and then we have so much better tools today than we had to the year 2000 when Uncle Bob created this. We have all of these we have compilers that gives us warnings, and we have Roslyn analyzers giving us tips on how we should do things better, and we have unit tests and automated tests that verify that changes we make don't break, and we have refactor help in Visual Studio and ReSharper and all of these different tools. We can do so much more compared to the early 2000s or even late 90s or 80s, when you made a change and it took forever to build and you couldn't actually verify that it worked until it was in production. So refactoring, don't be scared of it, and try to find these things seem to work together. They seem to be coupled together, and take a bit of single responsibility. Take a bit of what Uncle Bob is saying and say only listen to one person, only have one guy have input on your code. That's a pretty good idea as such. I just don't see one person. I don't see a C-level person ever. So, but aim for high cohesion. So what about open-close principle? Well, interestingly enough, open-close principle was coined by Bertrand Meyer in the 1980s in a book about Eiffel, which is a language. And in that book, he used open-close principle to justify, the book was about justifying or explaining this design choices made in the Eiffel language that Bertrand Meyer had written and designed. So literally, open-close principle has nothing to do with our idea of open-close classes and things like that. This was a principle that he put into a language choice, or a design choice he made for a language that he built for something that he intended to use, and that made sense in his world. And I'm not saying that it was wrong. I'm just saying that it's different than it was then. Today is different. And also, Eiffel has this interesting thing that if you changed a class, if you added a property to it, or you added a new method, any class, any library, sorry, I actually have a slide on that. Anything you made to change to a library, any client that used that library actually had to make updates to be able to use that code. So if you had written a piece of code and then distributed that to different clients, and you went in and you added a field or you created a new method on it, then that forced every client that depended on that library to make code changes, which is honestly terrible, but it's actually a versioning control problem. It's not a software problem, right? If they had proper versioning control in that language, you could have done things. You could have had one version and then you made changes to it and you reversioned it, and you wouldn't break things because clients could depend on the old version while you built stuff in the new version. But that's why open-close principle says whenever you have created a class, never make changes to it, always inherit it and add more to it. But it was based on the idea that they had to recompile and rework every single client that used that class whenever you made a change. We don't have that problem today, so it doesn't quite make sense. And also, if you happen to be like me and most of your code is not published on NuGet or NPM or some public repo where other people work with it, you can do whatever you want, right? Because you don't even have to go with semantic versioning. You can just rewrite the code. You rewrite the code, the compiler says, hey, you made a change here, it doesn't work with this thing over here. Cool, I'll just go over there and change it to whatever I need it to be. So unless you publish your code somewhere, you can do whatever you want. Open-close principle, yeah. No. It just doesn't work in today's world, in my opinion. We have version control and such that makes that go away, in my opinion. Liskov substitution principle, another very interesting one, and that's actually about behavioral subtyping and not syntactical compatibility. Barbara says this herself. She doesn't talk about syntactical compatibility and substitution at all. So Barbara Liskov worked with data analysis, and she was talking about behavioral subtyping when working with data. And what she's actually saying, if we look at what she's saying here, is anything that you can do on an instance, on a class or an instance of a class, needs to be possible to do on the new one. So basically, she's saying that if you can do QX, so if you can take X and pass it into Q, and Q will do what you want it to do, then you should be able to pass in Y if that is inheriting from the same type as X, and it should do exactly the same thing. It should not change anything. So according to Liskovs, your classes are not allowed to change at all. The functionality should be exactly the same. So behavioral subtyping basically says the behavior of whatever you're inheriting should stay the same. You're not allowed to make modifications. And this makes a lot of sense when you're working with data that Barbara Liskov was doing. But it had nothing to do with being able to subtype classes. It had nothing to do with trying to fit into the interface of your previous class. Nothing whatsoever. What she's literally saying in this piece of text here is, if you write a complete set of unit tests on your class, whenever you inherit that class, your new class has to be able to go through that exact suite of tests with green tests all the way through, because it's not allowed to change at all. You're not allowed to add more stuff to it, but you're not allowed to make any behavioral changes to it. So literally, Liskov substitution principle has nothing to do with what we're doing, and it doesn't say what we're saying that it's saying. So my version of it is, just don't break the contract. Try to look at some of the rules, because they do make sense. They do fit in pretty well, but Liskov substitution principle as a principle is wrong, because it doesn't say what we're trying to make it say. What we're trying to make it say, on the other hand, it can be pretty useful in some cases. Interface segregation principle. Well, as mentioned before, thank you, I think it was Lev, Levias said, if you have done the S properly, you probably don't need interface segregation principle. If your class is truly single responsible, there is no need to have separate interfaces, in my opinion. There might be cases where you want to have separate interfaces for limiting deletes and things like that. Absolutely, it could make sense from what you're building, but that's a contextual thing. That's something that you want to do in your code because your requirements have it. It's not a principle as such. And dependency inversion principle, well, that is just plain old awesome. I believe that dependency inversion is something that you should aim for. It's really, really useful. But we should also remember that it does add up to a more complex code base. It's hard to figure out what's actually what's going to interact when you're running your application. It is harder to read your application because, once again, it's only available at runtime when you know the full configuration. It makes it harder to jump between code because code A depends on interface B, which has implementation C that depends on interface D that it has implementation E, and so on. So jumping around your code base and figuring everything out can become quite tedious. And also, maybe we should look away a little bit from unit testing and do a bit more integration testing to make our code simpler. Do we really need to interface everything out into abstractions and do dependency inversion in every single case? I know the common thing that people say is, oh, if we ever need to switch out our SQL database for an Oracle database, we have to have an interface. Nobody makes that switch. And if you make that switch going from SQL to Oracle, it's a much, much bigger problem in a lot of areas than just, hey, let's just switch out the database layer and we're good. So in a lot of cases, we can probably get away from doing all of these complex things and have simpler code, and then basically make sure that our tests are more integration tests than unit tests. So we get away, make it testable, which is good, but we make the code more readable as well, at the cost of not having really granular unit tests. But once again, I come back to readable code is better. And maybe we should just look at KISS, keep it simple, stupid, or keep it stupid, simple, depending on who you ask, to make our code more readable. And I'm not saying that I'm smarter than Uncle Bob and everybody out there, and I'm not saying that I am right in all of this, but I do think we should look at things in a more critical light and maybe say, well, this was good 20 years ago, but maybe today we have other tools, we have other abilities, we have other features, we have other needs than we had then. That means that maybe we should challenge things. And I do believe that a lot of Solid is probably not worth looking at today in some respects. if you look at the actual principles. However, I do still believe that what we're trying to say with those principles is really good. The intent of the principles in the way that we have interpreted them is probably useful in a lot of cases, but we have interpreted things that aren't actually what we're saying that they are. With that, I just want to thank you all for listening, and I hope that you really got something out of this. I haven't heard a single question so far, which is, I don't know, either terrifying or fantastic, because it either means that I am the best person ever to present and you all understand everything, or you haven't understood anything and I'm the worst guy ever. But I do see there's something about the 5230 thing.
I think that we are running out of time right now, but we also have some time in the discussion zone
Yes.
on Zoom, so we can proceed with the discussion zone.
That sounds good. I will see anybody who's got questions in the discussion zone in that case. If you don't end up there, thank you so much for listening. I hope you got something out of it.
Thank you, Chris. Thank you, Maxim. Bye-bye.
Thanks,
Bye-bye.
bye.